Hello everyone. Alright, let's do it. We have a hard problem today. Shortest path, visiting all nodes. Oh, this is a new problem. Alright, let's do this. You have an undirected connected graph with nodes labeled from 0 to n minus 1. You are given an array graph where graph I is a list of all the nodes, so it's a adjacency list. Return the length of the shortest path that visits every node. You may start and stop at any node. You may revisit nodes multiple times, and you may reuse edges. But we just want to know the shortest path to visit all nodes. Wow. One, 0, 2, 0, 3. Huh. Let me think. A graph, I can take any node and it'll become the root. And I can turn that into like a, I was going to say tree, but it's not a tree, it's a graph. But anyway, from any node, right, I go out, and then I go out, and then I go out. Like, what if we do, like, say, BFS, right? Because we want to search everything. Man, BFS, DFS. Oh, 12. Length is 12. Are you saying we have to start from everyone and then try it? Well, what if we do, like, we'll go here, right? And then we have to go back. We'll go here and go back. Now here and go back. Right? That's starting from 0. That will be 1, 2, 3, 4, 5, 6. Starting from 1. 1, 2, 3, 4. No. 1, 2, 3, 4, 5. Right? 5. I don't have to go back. And we hit everything, right? So it's 5 steps. I'll go from 1, 1. I have 2. 2. Go back. 3. And 4. I hit everything. Come from 2. 1, 2, 3, 4. 1, 2, 3, 4, right? From here, from 0, 1, right? Now it's split. 2, 3, 4, 5. Right? 1, 2, 3. So I go back, so here. 1, 2, 3, 4, 5. 5 steps. But that is, but if you go 1, 2, right? So instead of going here, I go here. So which means from this I start. I need to find, hold on. I simplify the problem, right? Simplify. What if we only have one node? Yeah, n is 1. If I have one node that is 0, right? Because we, wait, shortest path, that's 0, right? So let's say, now this is one node, n equals 1. This is one node, but it didn't connect to anybody. So that should return 0. Yep, that is 0, right? So what we're saying, if that is 0, if I have 2, right? I have a 2, then I start from anyone that's 1, right? Now if we have 3, yeah, just draw it out. If I have 3, so if we have 2, right? Now I have 3, it must be connecting to one of them because it's connected graph. But It's also possible, like we can have one edge or we can have two edges. But anyway, if we have the third one, right? Then let's say those two requires one step. Now we add the third one, right? Which means from the third one, whichever node I connect, that shall be it. So if I have three nodes, it shall be two, right? Three nodes shall be two. So no matter how the three nodes connected, it shall be two. Four nodes. Yeah, if it's three nodes, it doesn't really matter. But now we have four nodes. Now four nodes have different way of connecting. Let's say we know the three nodes, right? We know the three nodes. And we say those three nodes, but the thing is, the three nodes, they are all connected, right? Those three nodes are connected. So we can say start from any one. Start from different ones will lead to different results, right? If we go here, we start from this, that's two. Start from this, that's two. But start from here, that's 1, 2, 3, that's 3, right? So starting from different node will give you a different result. That's true. Starting from different node will give you a different result. Why don't we simplify this, right? Why don't we simplify this? Let's find the ones with only one edges, right? And then I cut it, right? Let's try that. What's that called? That's called a something ordering. I forgot the term of this. So basically, we go through this and find a node that only have one edge, because for these nodes, there's only one way to go, right? There's only one way to go. Either they go in or somebody go out, and then that's it. So I say, wait, what do you say? I say pick those nodes, one of those nodes as the starting point, because this edge, if somebody goes to that node, right, it will be wasteful if have to go back, right? So the way to think about this is these nodes shall either be the starting point or they shall be the end. I mean, they could be, no, hold on, like here, like these are three nodes, right? They have to go to this. But anyway, one of them shall definitely be the starting point, because we save, right? We don't have to do the double thing. So let's say we pick one of them to be the starting point. Okay, so that will be the starting point, and then whatever it's linked to, that will be the new starting point. So if, okay, so this one is starting point. So for here, if there's a 0 or there's a 3, all right, as a here will be either 1, 2, or 3, and you'll find out it's like it's the same. Okay, so let's say I pick 1 as a starting point, and 1 to 0. So now we are at 0, right? So 0 goes to 2 and goes to 3, and we have one step. Now 0 is the starting point, right? So the 0 is the starting point, and 0 has two edges. So we need to pick which edge to go. And no matter which one I pick, because I know I have to go both sides, because it's starting from me, right? It starts from me. So I know if I go one side, I have to go back and then go down the other side. So how do I choose? Well, I shall choose because they are split, but they split, the rest might actually not be split. It might be connections, because it's not a tree. There might be connections. I mean, what I can do is, okay, I say I'll go down to 2 first, and then do whatever, and see how much it takes. And then I say I'll go down 3 first. So if I go down 2, what will happen? If I go down 2, that should be the minimum steps to visit the remaining, right? Visit the remaining. Oh, it's not really visit the remaining. Or can we just try to visit all the edges? And that's gonna take a long time, right? Because I have to count for all different possibilities. Like from this going down, like every time we choose one way, we have to figure out the entire thing. Because we were saying that different order makes difference. Different order makes difference. That doesn't make any sense, right? 0 to 1. Yeah. Yeah, look at this one. If it's 1 to 2, and then we have 3 and 4 in this, because from 2 I know I have 3 and 4. And it's always wasteful, because if I go this, right? So I 1, 2, 3. If I have this chance, I can always go this or go this. Huh. And the key is try to walk as little as you can backwards. So like here they're in one line, right? They're in one line. If I take this out, right? Now ones with 1 is here. But we cannot start from here. We pick the 1 and then we start here and then we hit here, right? And then from this, I can see I have many children. I have many children. How do I know which child to pick? Always like the longest path. Okay, like from here 0, 1, I go 2, I go 4. Then that's it. That's the longest path if we don't count going back. So that's like one way, longest path, or 0, 1, 2, 3. All right, I have 2 paths. And then also 0, 1, 4, 2. So I go 4, right? And I go 4, the only way to go is go 2. And I go 2, the only way to go is 3. So I can also have this, and this is longer. So basically, we can say, let's try to find the longest path starting from each node, right? So I say I'm at 0. I want to find the longest path. So 0 I see as 1. So the longest path involving 0 will be the longest path involving 1. So I say, okay, I'm now looking at 1. And 1, the longest path of 1, because I have 2, right? So I say longest path is either 2 involving 2 or involving 4. So I go 2 and 4. So now I have 2. So longest I have to go 2, but I came from 1, right? So I cannot go back. So I say, okay, the longest path for me is I have 3. So either 4 or 3. So I go to 4, right? And now at 4, what I see is, oh, so there's another way to go. So longest path to go for 4 is 0, right? So now go 2, 2 is 1. Go to 3, 3 another way to go, so it's 1. So longest path to go from 2, based on this condition, is a 1, right? Is 1. But if it cannot take 1, is 1. And then, so 2 is 1, and if we go 4, again, only these two are taken. So we're at 4, right? And when we are at 4, 4 sees 2. So I say, okay, 4 I can go to 2, right? So now I have to go 2. So in this case, 2, 1 is taken, 4 is taken. There's only 3, so I go to 3. Now the thing is, because, the state, the state, because there are only 12, which means I can use a bit mask. If 12, yeah, we can use a bit mask to, technically have to use 3 because, no, why use 3? It's 12. 12 bits, right? It's 12 bits to represent the state of which one has been visited, right? And then on 2, I get the longest I can go with 2, right? And then, okay, so now that we figure out how to represent the state, why don't we just go directly to compute the path, the shortest path? But yeah, it's hard to explain the shortest path. So I'm kind of converting the problem to the longest path we can have, starting from a node, right? Like starting from 2, given this state, the longest path I can have is 1, right? So from 4, I have 2. So going from 1, right, I say 1, the longest path I can have is either going this and this. And going 2, I can only go 2. Going this, I can go 3. So I say longest path starting from 1, right, with this condition is 3, right, is 3 passes. And so I said the longest to go here. Well, I shouldn't say longest path, is the most nodes I can visit. All right, the most nodes I can visit. So from 1, the most nodes I can visit is right? That's the most nodes I can visit. And then, actually including myself, right? Including myself. So now coming back to 0. So what 0 sees is if I start from 0, the most I can visit in one pass without going back, right? The longest path, then from 0's point of view, is returned by 1, which I can go 1, 2, 3, 4. I can go 4. And then I compute 0. So I say, starting from 0, the most I can visit in one path is everything, right? So now I have that. Remember that. Okay. So in that case, hold on. So we have the state, right? We have the state. And we have, we have the state, say, starting from 0, the longest I can visit all 5 in one shot, which means the number of nodes I can visit is the number of paths. 1, 2, 3, 4. No. So this is nodes I can visit. So from here, the nodes I can visit is 5. 1, 2, 3, 4, 5. And the path is 1, 2, 3, 4. 4 paths, right? So I can visit 5 nodes and 4 paths. And from 1, right, I can visit, I don't know how many. This is 1, 1, 2, 3. I can visit 3. Right? I can visit 3 in 4 paths. Because I can go here, right? Because 1 is here. yeah, I just have to do the same, repeat it, because this, I won't know, right? I'm starting from 1. Oh, hold on. If I have done 0, right, and when I go to 1, so if I have a node, I then find out everything that's starting from this node, I already know. Now I go to a second node, right, and then I say I start from that node. Then if I'm starting from that node, so that will be the state, right? That will be the state. Now I have to recompute, which is fine. Okay, we'll just recompute. So from here, so the longest I can say is also 4, is 3, right? 4 nodes. 1, 2, 3, 4, 4 nodes, which is 3 paths as the longest. And from 2, if I'm starting from 2, and that will be slightly different. I have 1, 1, 2, 3. 1, 2, 3, 4. That's 4. So from there is also 4. Right? And from here, it's going to be 1, 2, 3. Yeah, that's also 1, 2, 3. Right? And from here, it's 1, 2, 3, 4, 5. So after we go through everything, what we get is the longest path that you can get starting from each position. Right? Starting from each position. Now, if the number you can, bless you, if the number you can do is the same as the total number of nodes, right? If the same as the total number of nodes, then we found it. If not, like here, from 1, I can go 1, 2. I can only visit 2. Right? I can only visit 2. And from 0, I can only visit 1. From 2, I can visit 2. From 3, I can visit 2. So none of them can complete. But then what? Then I say, if I go from 1, right, the maximum is 2. Then I want to know, so like from 1, let's say I can visit however many I have. And we also need to know along the way, right, along the way. And then from a certain position, right, from certain position, what's the longest it can go, given that the rest is all visited. Hold on. State is all 0. Only I have visited. And then, right, that's the starting point. So we have the starting node and also the current state, right? So the question for me is, given a starting node and a current state, given the starting node and the current state describes how many has already been visited, right? Which we can do very easily. Count 1. And my question is, right, given that, then my question is, how many how many steps is required. How many steps required to go from this to visit the rest? Okay. Okay, so this is the current state, and I know which one has not been visited. And from this point, and I want to know how many, right? And then if it's not possible to visit all of them, then I can return, like, say, -1, something like that. If it's possible, and then I will return the total number of steps, right? Go from here to visit the rest. Okay, so coding wise, let's say I pick a starting point, right? And then it has no matter what, how many. And then I go here, right? Go to one of them. And now that my state is, this is the starting point, and I have a state, it's just one. So I'm going to ask, what's the total number of steps needed to visit the remaining, right? Once we're done, I will just add 1, that will be the starting point. And we go here, it's the same thing. And then from this, it'll be the same. So when we're here, I visit this, so the state changes. So I go here, so we're starting from here. Now, starting from a state, hold on, starting from this, I visited, so my state is already like 0, 1, 0, 0 something. So I say, in this condition, right, what is the steps to visit the remaining? So I say I go to my child, right? I go to my child, and I'm going to pass this state. I pass this state and my current. So I haven't visited yet. So it's given this is the starting state, and I want starting from this point, and I want to see how many steps I needed. So from this, I will do myself and go here, right? So kind of just recursion, and eventually I will compare, right? So I should return like the infinity, right? Positive infinity. That just means this path will not pick. Let's try this. Let's try this. This might work, but it'll be very interesting if it works. I need to see the code in order to keep thinking about this. All right. So what we saying? What we're saying is def dp, right? What we want is the starting point and the state. And this one will return int. Right? So let's call it begin. So it won't be messed with state. So begin is a integer. Right? That's actually, for this I should say n equals to line graph, right? So begin is an index, right? The index. So when we call the begin, this shall not be in the state, right? Therefore, what do we need to do? What we need to do is go for all my child, right? Go for all my child and see if it has not been visited before, right? And I try that child, right? And then try that child. So, okay, so let's say for child in graph back, and we compare the state. We say if state right shift child, right? The state right shift child at 1 is equal to 0. That means this child has not been visited before. So I need to do dp this child at state or 1 left shift child, right? So I do that. So this will tell me the longest path, the number of the minimum path needed to visit the remaining unvisited state. But of course, this is actually not child. I just realized this is the it's called parent, par. Yeah, so it's the parent. And if this child has not been visited before, then I'm going to visit this child, and also this is to signal that the parent has been visited, right? So this will give me the result. I'm going to say the main path, right? Main path. I'm going to start with math.infinity. So I'd say import math, right? This is math.infinity. And for each one, right? For each one, I say main path shall equal to the minimum of main path, what we already have, and this plus 1, because it's the one path as I go out, right? If not visited, then we do this. And if I visited, then we don't do. And eventually, how do we determine if there is a path, right? If there is a path, hold on. No, it shall return. Yeah, because in this case, let's say 1, all right, and go out to 0, and 0 go to 2, and 2 I cannot get a 3. Right, 2 I can never get a 3. So 2 will return positive infinity, and that's not right. That's not right. How about we return the state? Should we return? So the current state is this one has not been visited, and then we have whatever has been visited. And from this position, I want to see the minimum path to visit as many nodes as possible. And then, like, there are two objectives. One is I want to minimize the number of nodes, and the other is I want to know how the maximum nodes I can visit. Okay. Have you tried?
I'm scared.
Okay. Cheers. Just salty. Yeah. Okay.
I don't really taste the thing inside. It tastes like olive.
Just olive, yeah. Yeah, can save on the seasoning. Okay, this doesn't seem to be working, man. Because what do we need to return? You tried it?
I think made it over.
Doesn't like olive.
Should I put it in the oven? No.
guess you can. I think you can. You can try it. We'll try one batch, see how it looks like. All right. So from any node, I have the state, which is the current, how many nodes has been visited, right? So starting from this node, what do I want to find? I want to find out from this node, is it possible to visit all the rest of the node? If it's not possible, nah, that doesn't seem to be a good objective. I can visit all the nodes, right? I can definitely visit all the nodes, but there are a lot of choices. Yeah, like in this case, right? I'm at 2. Let's say 0 and 1 have been visited. What is the maximum I can visit? I can visit all of them, 3 and 4. Should I return the shortest distance to visit all these two? The shortest distance to visit. The shortest distance to visit. The total number of choices, just because each node is either visible, so it's 2 to the 12. That's not that much. Can we just, I don't know, find out all possible states? Okay, so let's say we have a certain state, certain nodes has been visited, right? And then I want to say, okay, so in that case, if I starting from this node, yeah, let's say 0, 1, 2, 3 has been visited, right? Now I have 4, and I starting from 4, I want to visit the remaining. What's the minimum? Yeah, I want to visit the remaining. What's the minimum? How do we find the remaining? So I want to visit the remaining. What is the shortest distance to visit the remaining? And then from 4, what we say in this case is 0, right? Yeah, from 4 is 0, okay? So 4 and that value will be 0. So if we can create all this, so like given a current state, right? And I'm starting from this node, whatever node I'm starting from, and I say I want to visit the remaining, all of them. I don't care. I just want to visit all of them, and I want to use the shortest path to visit all of them. Okay, how would you proceed? So I'm here, right? And if my children is like, if none of my children right? If none of my children has not been visited, right? That means I can never visit. I can never get to. I can never get to. Hold on. If I am a certain position, and I know, right? Because if I'm passing this, then this one has not been visited before. So I visited this, and if I visited this is not enough, then I go to my children, right? And if I go to my children, I want to find a path to visit all the remaining, right? I want to visit all the remaining, and then give me the shortest path I can visit all the remaining. If I cannot, then that will return negative, return infinity, right? Okay, so this means if state right shift, I don't like parent, current, okay? Let's call it current. This is current. If state if I right shift current, if I right shift current, right? If state right shift current, no. I have to go new state because I'm visiting. So I say new state equal to state, right? And the state and one left shift current, and we say, right? And we say so n is this. Full, bless you, bless you. One left shift n minus 1. So I say new state is this. And if new state is equal to 4, then I return 0. Right? If it's not, then I set min path equals this, and I go through its children. And if its child is a 0, right, then what I do is this is the current state, new state. I don't like new state. Let's call it current state, right? So go to the child with the current state, right? With the current state is visiting this, where we'll go to the child with the current state, and it shall be dp this plus 1, right? Just talking about path, the main path, and no matter it's going to be if it cannot visit. So the goal is to visit the remaining everything, right? We want to visit everything, and we'll visit all the children that. Yeah, but some maybe I cannot go to everything, but that's fine. Right, that's fine. And we simply just let me think. So those children, right? So I try to visit everything, and then it will tell me that child and current state plus 1, right? Okay, that's the minimum path. Okay. And when it's done, apparently, because when the passing, I have a state and a current, right? And I fill that state and I have the remaining ones. So I say, if I can fill out the remaining ones. That's basically the question, if I can fill out the remaining ones starting from me. And the answer, let's say in this case, is I cannot fill up. That's fine, I'll just return minimum path, right? Let's say let's return minimum path like that. And import cache. Now what I want to do, is to iterate through all the states. Okay, I want to iterate through all the states instead of going this. So what I want is the full state. Actually, it's not a full state. It's going to be from here, right? So what I want is, I don't know, what's the, I want to observe some stuff. Let's say 12, right? Let's say for I in range, let's say 100. Now, 1, left shift, this is what we're going to do. Left shift 12 minus 1. Right, we're not going to start from there, so it's going to be minus 1, right? To what? To 0. Okay. I in this range. Let's just print. Okay. I'd say I shall be 12b. That's not what I. Hold on. About 0. Maybe 12.0b. No, it says 0, 12b, right? Yep. 12. I'm going to remove. I'm going to move these. Maybe it'll work, maybe it doesn't. I'll be back. All right, back. Just finished an important business. All right, still clueless. All right, still clueless. It's been an hour. What I feel like is when we iterate through the state, I cannot just go numerically. Right? That's what I think. Let's say if I have 5 states instead of, let's say 12, right? We have 12 states, 12 positions, right? So the first round, I'll pick any one to be 0. And the second round, what I think is I can leave the first one as 0 and pick any one as 0. Right? That's what I think, because I need to make sure that for every state that we visit, we have a previous state that's already been filled. Okay, let's try this. I think this is fine. So what I want to try is, given the full state. So that's the full state. I don't want to change it. So what I want to do now is, I have n. So for, let's say, for I in range n, right, so I want to iterate through all the states. And all the states. Don't do 0 yet, right? Don't do 0 yet. So the last one shall be the 1, 1. I will say, okay, I'll pick this, and the 1, that is to go through all the states. Wait, is that all the states? That's actually not all the states, right? No, that's not all the states. It should be occupied, and I would say blank, right? And then it should be 2 of them occupied. 2 of them not occupied, but a 2 of them occupied could be the first one, blah 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 blah, and then second one, blah 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 blah, third one, blah blah blah, fourth one, blah blah, and then 3 of them. How do I generate? Well, if it's 12, I can actually generate. I can generate all the states. All the states? All the combinations. What I want is combinations, right? Just combinations. Let's see, 12, right? The maximum will be, say, 12 choose 5, 2 choose 6, 900, which is fine. So now what I want to have is for I in range, let's say for R in range 1, I want combinations. So from itertools, import combinations, right? So from 1 to what? So like, so how many is open, right? How many is open? How many is open? How many is open? So 1 is open, 2 is open, and that many is open. And then eventually is all of them are open, right? Eventually is all of them are open. Then I should not do the cache here. I should do the DP myself. And this just DFS. Let's do DP. Alright. Starting position is going to be, say, math.inf times something times the length. It shall be what, total full, right? That's the total states. Yeah, and then for this in range n. So that's the dp, right? And we say if state is equal to full, current state is full. That means, wait, hold on. What are we talking about? Current state is, state, I don't like this. Let's do it this way. If this is equal to full, then we say, first of all, is the state. So we say if this is if dp current, not current, yeah, if dp current and a state is smaller than math.inf, which means it has been visited before, then we just return dp current and a state. Otherwise, I check. If when I fail this, everything is good, then we simply say dp current state, right, is equal to 0, and then return 0. Otherwise, I have the min path. And for this, min path is blah blah blah, and eventually, right, we're gonna say what we're gonna say. We're gonna say I need another thing. Let's go -1. If it's smaller than 0, if it's larger than 0, right, larger equal to 0, which I think math.inf is larger equal to 0, then we simply just return this, right? Otherwise, blah. Otherwise, I'll say dp current state shall equal to min path. It could be math.infinite. That's possible, right? And then is I'm trying to get so these are like the open spots, right? Those are the open spot. Okay, so from 1 to what? To n-1. Right, so trying to get, so these are the open spot. Well, actually it's to n, right? It will just be everybody, and I just have everybody in it. But that's when we have to find the minimum path. Yeah, so to n, right, to n. So we do this, and then we're gonna say for starts in combination. All right, combination will be, so what's the combination? Well, let's say nodes shall equal to list range n, right? So combination will be nodes choose r. Right? Let's see. Go here. From iter tools, import combinations, right? Let's say nodes equals list range 12. And for starts in combinations nodes, let's say 4, print starts. Yeah, I think this is what we want, right? This is what we want, all the combinations. Okay, so now we have all the combinations starts. So we just basically throw the current state, right? Now we're going to create a current state. So the current state shall be everything except for these shall be empty, right? These shall be empty. So the current state will be for s in starts. So current state shall equal to 4. We call it state shall equal to 4, and then state exclusive OR, right, equal to 1 left shift s. Right, we just turn those two, so that will be my new state, and then we simply call DFS. Right, we call DFS. Call DFS current. So again, so we create a starts, and then for s in starts. Right, so I say I want to go with s and a current state. Right, so this will give me if I have these open spots, everything else has been filled. So from this start, how many paths I need to fulfill everything. But what if I cannot? Like at my current position, right? And I cannot, and I go, and everybody, all my neighbors are all visited. So yeah, so now I return math.inf. So for this, I just basically fill out the DP table, right? And for everyone, I tried it for everyone, I tried it for everyone, try it. And for different numbers until n minus 1, right? Until n minus 1. So once this is done, so start the state, right? I'm going to run one more time. Let's say this time is going to be the entire thing is open. Let's just say for s in nodes, right? For s in nodes, so we can start from every one, and we say DFS s, and now let's start with 0, right? And then we want to find the minimum of this, and I'm going to return the minimum. Okay, let's see if this works. Okay, so I have just a graph. Output should be 4. Output should be 4 as well. So I have is graph, shortest graph. Try it. List object is not callable. DFS. This one passed, but this one failed. I return. That is interesting. Okay. Let's print out. Actually, we can do n plus 1. Right? We can do n plus 1, and then we just return minimum dp. Well, actually, hold on. Each row is the state. Each row is a current, and this is the state, right? So I have the first. Should be the first column. Right, first column for j in range n. All right, first column dp. First column 0. It's not first column. Stay. Yeah. So stay. So dpj, that should be I, right? That should be I 0. Yep. Okay. So now I can print out. Let's take a look at the dp. For row in dp, print row. Okay. So I have 4, right? So 1 left shift 4 is, so 1 is 15. Right, so I have 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, that's 15. And it doesn't look good, right? That's fine. I think what we can do is basically print this after each. And just take a look. Oh, the minimum. What if it's -1? Okay, I want to say this if dp I0 is larger or equal to 0, else 0. I think I can just do times this. It's not helping. Okay, now we have something to analyze. All right, let's take a look. So that should be the first. So what we're talking about, the one we have is, if I remember, 0, 1, 2, and 3, right? So the first round is, we'll pick actually I like to print a state as well. Okay, so just print the state. Okay, so now I have the state. Shoot. I should go this state. Oh, this one has 4, right? So 0, 4b. Okay, so I start, yes. I think the states are fine, all right? So that's the first state. The first state, I only have 1, so I pass this into it, it gives me 0, right? That's just the first node, 0 node, that is 0. So this is 0, this is 0, and this is 0, which is fine, right? So far so good. Now next, so this one says I'm gonna have, so I have 0, 1, 2, 3. So 0 and 1, right? This is basically 0 and 1. So 0 and 1 are open. If 0 and 1 are open, what are we doing? I say, so I want to pass into here for S. So I have the current state is 1100, right? And I want to pass in is current, I believe it's 0. So I have a 0 and a 1100 pass in, right? And then I say if, that is not correct. That is not correct because I just returned this. Hold up. DP and the state. state shall be, no, hold on. So state is this, right? This is 8 plus 4 is 12, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right here, I have a 1. That's too much minus 1. I can't even see. Okay, so I have a 1, right? Oh, it's hard to see. Can I do like negative infinity? Oh, now I have negative infinity and then positive infinity. Nah, that's not easy to see. It's actually, if anything, it's actually worse. Maybe not, but I can see the ones. Okay, so we're saying here, we'll change it to -1 later on, doesn't matter. So now I say I'm at this position, which has not been visited before. So I turn this into 1. Okay, so I have 0. So which means, this means, right, in this state, right, in this state, if I start from here, it'll take me 1 path to visit the rest. And if I start from here, which is 1, it will take me 1 path. So this is fine, right? Now I'm looking at here. This is 0, 0, 1, 2, 0 and 2. So 0 and 2, if I start from 0, in this state, that's 1. 2, that's fine. 0, so 0, 1, 2, 0 and 3 should be the same, 0 and 3. So it's here, 0 and 3. That's also fine. And this is 1 and 2. Now this is the problem. 1 and 2, this is the problem. So I'm at 1, and we're saying 0 is visited and 3 is visited, right? So I'm at 1, and I'm trying to see what's the longest path, and I say I cannot, which is true, I cannot, because 0 is visited. 0 has been visited before. So if 0 and 3 has been visited, and I'm at 1, right, and I visited 1, and I say I don't go to 0, because there's only a place I can go. So the question is, if I visited, then I go to 0, right? In this case, the state is only this one is open, and the rest is all visited. But I cannot. But yeah, so this one remains infinity. That's the problem. I need to go to the rest. So let's say I go to 0, okay? And I want to find out to go to 2. How do I go to from 1 to go to 2? I'm at 1. I can go here, but this one's visited before, so I cannot go. Therefore, I say from 1 I cannot go to 2. But that's not true. I can go to 2. So like in this case, with these two visited, from 1 to 2 still requires 2 steps. I shall return 2. It requires 2 steps to go to 2. So if I go to 0, so it should be from 0. What is the minimum? Hold on. So this shall be solved if 0 is empty. Only 3 is visited in a 1 and 2, right? This can be resolved from 1, 0, 2. That will give us. So that's the state. So what we're looking at shall be, if it's 1, 2, 3, 4, 0, 1, 2, 3. So 1, 0, 0, 0. What's the minimum steps needed? Okay, hold on. We go 1, 0, 0. Yeah, 1, 0, 0. What I find out is if I start from 0, 1, it takes 2 steps to finish the remaining. So if it was 0, 0, 0, all I find is 2, which means starting from any position, right, the maximum I can get is 2 steps. We can go to a certain state, which means we have to repeat. How do we build a repeat? So this tells me from any starting point, right, I can take 1 step, right? I can take 1 step to visit, to get to 1 node. And if I'm starting, so that's 0. From 0, I take 1 step, I go to these 3 nodes. From 1, I take 2 steps, right? 1, 2, I can visit 2 nodes. And 1 step to go to 0 node. And from each one, like this. But, the thing is, what I need to do is from here, so let's say from 1, I can take 2 steps to visit those nodes. And what I want to know, bless you. So, okay, let's say from 1, right? Let's say from 1, and I can take, I don't know, whatever number of nodes. So I can take 2 steps, and I can get 2 nodes. So I find this one, okay? So I find this one. Then what? And then I need to know at this 2 steps, so which 2 nodes has been visited, right? Okay, let's say 0. Let's say 1, 0, and 2 is what this one represents. Okay, so I can visit these 2 nodes. So when I go to, so like now I say from 1, right, I can go to 0 and I go to 2, but so I can visit these 3, but the 3 is not able to visit. And then I can say I go to either 0 or 2 and count. So if I go to 0 or 2, right, and take it out, right, and then we have this state. We see how much we need. So like these are done. So we have, this is empty. So we start from here. So we go to that and find the state, right? We find the state, and what we say is, we find a state, and then we say, yeah, so that is a state, right? That's the state. This is empty and this is empty, right? So what is your suggestion? So my suggestion is, right? My suggestion is we go through everything, right? And then we look for this. Remember, this is a 0, right? So everything is 0, and this is 1. So right, these are just different states, right? Just different states. So we just say from each starting point, I loop through the entire thing. I look for this, right? I look for this, and this will tell me that I can hit. So from this, I can hit like a one step. I can go to another one, and then I just say from all the other one that I can hit, right? All the other one that I can hit. All these ones that I can hit. From each of them, I will create a new state. Basically, it's just this state, right? So basically, it's this state. Okay, so I have this state, and this state is a starting from this, and if I have this state, and I'll take 1, 2, hold on. This doesn't make any sense. This is the 0 state, right? So this just means if I start from 0, I don't find anything, right? So I start from 0, I cannot go to all of them. So if I go here, this is just like if I start from this, right? This is 0, 0, 0 to start from this. I can now visit all the nodes. And this is 1, right? If I have 1, this is a new state, right? That's a state. What is a state? This state is 0, 0, 0, 1, right? That's a 0, 0, 0, 1. So the 0, 0, 0, 1 state, what we're saying is 1 is good, right? And now we want to see, starting from here, can we hit the rest? Why is this infinity? Hold on, doesn't make any sense. Let's say I start from 0, 0, 1, 0, right? That's the state, that's the current state. 0, 0, 1, 0. And then I can start from here, here, and here. So 0, 0, 1, 0, so 0, 1. So 1 has been visited. So now I start from 0, right? I start from 0. So counting in, 0, and this is 2, right? This is 2. This is 2. So I look at 2. I start from 0. Right? I start from 0. And I want to know at the current state is 2, so 0, and current state is 2. Can I visit? I cannot, because I can only do 1 and then that's it. I cannot. And 1 is infinity because it's excluded. It's already set. Alright, it's excluded. So here is starting from 2. So starting from 2, I'll take 2 steps. I can visit the remaining. Right? I can visit the remaining. 2 steps. So I can visit 3 nodes. Right? I can visit 3 nodes. This is only has 3 nodes. So let's say I'm here with 3 nodes. And then for this, if the 0 is, then of course, if the 0 is visited, then they cannot visit anybody. And then it's 0, 0, 0, so I say, okay, if it's 0, 0, 0, I try to go here. So this is this, so they all have, this is all infinity, and then we go 1. If I visit 1, so we go here, right? And then, so 1, so I'm at 2. Wait, hold on. I'm at 0. So if I'm at 0, the starts S shall be 0. So it's a 0, 0, right? So if it's 0, 0, and it's minus infinity, okay? So I'll set it to 1, which is the state. No, actually not, which is 0, 1, which is all these. And I will try the child, right? So its current state is this, with 1, that's infinity. Right, that's infinity, so that's all infinity, so therefore that's infinity, which means from 0, go out, you can never go. But how about from 1? From 1, right? Okay, so from 1, that will lead us to 2, right? That will lead us to this situation, this, right? So it's different. It's just gonna be 1. 1 is taken, should be here, right? It should be this one, and then I say I'll go to 0. So now we're looking for 0 and 2. That's infinity. 1 and 2. Oh, I cannot do 1 and 2. Oh, 1 can only go to 0. Oh, that's why that's also infinity. Because from 0, in that case, I cannot visit everybody. Which makes sense. Okay. So basically just means we start from here. We can never visit anyone. That's why it's all infinity. Okay. That makes sense. Right? That makes sense. So this is, so we know, and it's 0, we can never go. And if we have 1, right? 0, 1, we can never go. But if we have this one, 2, so we need to find, right? We need to find a starting position. This is like, we all have starting position. We're gonna start every single one and see how it goes, but they can never do, which means they never go. So we can, okay, as I said, let's start from one of them. Okay, I start from here, right? I start from 1, this state. So we're looking for this state. So this state basically says, if I choose 0 as a starting point, okay, and then I have the remaining, and see how much I can get, and this is 0, nothing. Okay, now I say we choose this, okay, 2 as a starting point. Now when the 2 is a starting point, then what we see is I can make at most 2. So I can make 2 paths, which means connect 3 nodes. Okay, so in here 0, 0, 1, 2, and that's 2 is the starting point. I can make 2. So I find out. Can we find out which 2? All I know is it's starting from 0, 0, 1, 0, right? And after 0, 1, 2, if I start from 2 and with 1 visited, I can visit 3. But I don't know which 3. All I know is I can visit 3. We actually also return if I know which. Oh no, this means I can visit everyone. This is the minimum path I can visit anyone. Which means at this, yes, that's visit everyone. This is to visit everyone, right? So in this state, I say I can, starting from 2, I can visit everyone except for except for 1, right? Except for 1. So this one said 1 is already visited, right? And then from 2, I can visit the remaining. So now the question is, how do I visit 1? Right? How do I visit 1? So we go to 1 and we find out. So okay, so this is starting from 0, 1, 2, right? So now from 2, I can visit everything. Everything's already done. So the only thing that's not visited, right, is we assume that have been visited is 1. Right? So what do is we just try to put 1 into the whole system, right? Put 1 into the whole system, which means because this 2 means I can go 1 path. This is a 1 path. 1 path visit everyone. And then whatever 1 needs to connect to this, need to add 2, right? Which means I should just go state by state, right? State by state, and find the. What if we have like also infinity, and then the first one that come up? Yeah, what if it's only possible to visit, like we have 2 nodes that cannot be included, right? Now we have 2 nodes that cannot be included, and everything else can be included. So we need to visit those 2 nodes. What do we do? Because if we think about this is a full path, right? If we think about this as a full path, and these nodes are just extension, like extends out. And if we go from large to small, right? Basically, that's what we're trying to find. We're trying to find the current state. Yeah, we can just go through. Like if it's 1, that means all the others, let's say, must be. Hold on. I go through every single one, right? I should go from the largest to the smallest. How do I go from the largest to the smallest? Right? Basically, it says if this minimum is not an infinite, we return that. Otherwise, we need to find. I mean, we can keep track on the maximum value on this one as well. Yeah. And I do think, because we want to find a minimum overall path, so we need to find a maximum that can keep everything, right, intact. So we find everything like that, and then we just, but wouldn't that be the same for everyone? Because the nodes that's not included in the path, they're just like on the outside, right? On the outside. However many they are not included in this path, but they have connection towards this path. And if it can be included, it's already included. The reason they're not included, this means they are just sticking out, right? They're sticking out. Now, if they are sticking out, that means, and if those sticking out are connected as well, might as well be another one, right? So I have to go out and come back in. Or I can pick this, right, and then go out, come back in. Which means if we can keep track of the largest value, we just find the largest value in this DP table, and I'm going to return. Okay, so this might be wrong. This actually might be wrong, but let's try. So what are we doing? What are we doing? We were doing, because I do return a minimum path, which means I can just keep track on here, right? Like, let's say the longest path is equal to, I don't know, 0. And then blah, blah, blah. And then this one will just return. We can say longest LP, okay, longest path. Okay, so this will be, say, longest path equals to maximum longest path on this. All right, and then once we're done, we get the longest path. And longest path plus 1 is the total number of nodes that can be included. So we shall return total number of node minus longest path. So these are the nodes that cannot be included. So they have to go out and in. Let's say times 2 plus longest path, like that. And let's not print anything. It's gonna be nan. Huh? How? Oh, maximum. Hold on. Maximum. Min path MP, shortest path SP equals DFS S state, right? And then we say if SP, right, it's smaller than math.inf, then we do this. SP. What the hell? How? That shall be 2. Oh, -1. Because the longest path plus 1. Okay, so that is my new effort. Okay, let's try this one. See how it goes. And of course, I don't have to do it. I can just do -1. That's fine. Oh, if I fail, then we are going to give up. Oh, use test case. Yeah, that's a good test case. I mean, actually, I can try it here. All right. This shall be 0. And of course, let's say, no, I cannot connect to myself. Let's say this, 1. This shall be 1. Uh-oh. We already find a error. That's one path. Expected roll of... Oh, my bad. Yeah, it has to be this. So it has to be 0 to 1 or 1 to 0. Right, and this is 1. I'm gonna try. Do we dare? I got a wrong answer. Yeah, I guess it's not 100% correct. All right, I mean, yeah, we got stuck. All right, I think I'm gonna check solution, but that's one last push. Okay, let's get one last push on this. The last push. Let's find out. 1, 2, 3, 4, 5. So I have 7 nodes, right? So 0 goes to 1, 2, 3, and 4. And 1 go to 0 and 2. 2 go to 0 and 1. 3 go to 0 and 5. 4 go to 0 and 6. 5 go to 3. 6 go to 4. Okay? So with this, with this, what's the longest path? 1, 2, 3, 4, 5, 6, 7, 8. That's my take. That's my take. But 1, 2, 3, 4. 1, 2, 3, 4. Hold on. 1, 2, 3, 4, 5, 6, 7, 8. Hold on. 1, 2, 3, 4, 5, 6, 7. Ah, we can do this. I see. Holy guacamole. How do we handle that? 2, 3, 4. Right? So 1, 2, 3, 4. Now these two are, it doesn't go out this way, but what we can try is, let's say this is visited, this is visited, and this is visited. Now I want to find like visited, visited, and a visited, right? So these 3 are visited. So starting from here, 1, 2, 3. We need 3 to visit the remaining. but how do we know, right? So basically we just say, okay, we find a path that connect the most, right? I will find a path that connect the most, and then once I find the path, right? Once I find the path, it could be, right? So this is the path with all the nodes already visited. I have 5 nodes already visited, so I have 2 nodes left. So I can say, take any node, right? Say take any node, and or we can say what we want to find is the shortest path that can connect these 2 together, right? The shortest path I can take these 2, which just means, let's say, everything else is visited except for this. Can we connect these? 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 If the answer is no, but then with all this, now we have to do, combinations again. Like, because it could be connected to one of them, they could be like separate, or no, we just set them because it has to be. It can be like 2 of them, right? 2 of them. So like we have these 2 open and these 2 open, and say we're starting from here. Can we visit? Now the answer is no, I cannot. Alright, screw it. We tried. Didn't work. Solution. Wow. EFS or DFS? Alright. DFS. Alright, I think I don't have to keep. I'll read this. Yeah, I'll be fine. Alright, see you guys tomorrow. Adios.